Good day and welcome back for part 2 of our discussion on inverse functions. Let me just begin with a few reminders from our previous video. We reminded ourselves how we define a function and we built up to the definition of an inverse function. And what we saw is that in order for a function to have an inverse, it must be what we call one-to-one. And from a very intuitive perspective, a one-to-one function has a graph that passes the horizontal line test, which means any two distinct inputs will not have the same output. That is to say, f of x1 will not be equal to f of x2 whenever x1 and x2 are different from each other. And if a function happens to be one-to-one, then we are guaranteed that it will have an inverse function, which we denote by f superscripted with a -1. And that inverse function is specifically defined to undo the function. That is to say, f inverse of x is equal to y whenever f of y equals x. And once again, intuitively, how we should think of an inverse function is it undoes the function f. In an upcoming video, we will be looking at a formula for the derivative of an inverse function at a point. And that formula will require us to be able to evaluate an inverse at a point. So let's explore several examples doing just that and work our way towards some general facts related to inverse functions. So a very common type of example. If we have a function, let's say 2x plus cosine x, can we determine the value f inverse of 1? And I prefer to think of this in the following way. F inverse of 1 is the quantity that we are hoping to determine. So what value will go into this blank space? We remind ourselves that f inverse is defined specifically to undo the function f. So whatever value f inverse of 1 is the same value that makes the function f have an output of 1. So if we take our function and set it equal to 1, the question is, can we determine any value of x that will solve this equation? And this is a hard equation to work with algebraically, so instead what I would encourage you to do is to just think of common values. And in this case, if x is 0, cosine of 0 is 1 and 2 times 0 is 0, and the only solution is x equals 0. And because f of 0 is equal to 1, f inverse of 1 is equal to 0. So when it comes to working with an inverse function, specifically the value at a single point, what we would like to do is restate it in terms of this more familiar idea of what input will make the function equal to 1. With that in mind, I would like you to pause the video, give yourself a few minutes, and for the function x plus the square root of x, can you determine the value of the inverse of g at 6? And hopefully you've paused the video to think about this. Let's just follow the template that we have above. G inverse of 6 is going to be some quantity, and specifically it's going to be the quantity where g of that value is equal to 6. So just restating this in a simpler form for us to work with. So can we determine a value of x where x plus the square root of x is equal to 6? And by inspection, note x equals 4 is a value that works. And because g of 4 is equal to 6, the inverse of g at 6 must be equal to 4, because the inverse undoes the function. So just to summarize, g inverse of 6 is the number 4. And as I indicated, this is something we will encounter in an upcoming discussion, so we will certainly get more practice. But for now, let me ask a different question. In this previous example, we were being asked to find the inverse of the function g at a value of 6. And you might be wondering, how do I know if this function has an inverse or not? And specifically, because this is a calculus course, I would like us to think of past properties of calculus we've encountered, maybe how a derivative affects the shape of a graph, to see if we can somehow use calculus to explain why this function has an inverse. So maybe pause the video for a second and think about that. And hopefully you've thought about this for a moment. And let me just note and make an observation to the left. I'm not going to try to sketch this specific function, but instead, if I was to graph some random curve that maybe looks like this. This is a function that very clearly passes the horizontal line test. You draw your favorite horizontal line, and it will intersect the graph at most once. And note, for the graph that I've drawn, as you move to the right, the function outputs are always getting larger and larger. And in fact, if a function graphically behaves in this way, that is to say it is strictly increasing, then it must pass the horizontal line test. Similarly, if it's strictly decreasing, it must also pass the horizontal line test. So let's just note this as an observation. If a function f is strictly increasing or decreasing, then it is 1-to-1. Its graph must pass the horizontal line test. So we're kind of just making that observation. And let's even take this a step further and recall what we know from Calculus 1. If the derivative of a function is always greater than 0, that would tell us that the function is always going to be increasing. If the derivative of the function is always negative, that would imply that the function is always going to be decreasing. So let's think about the derivative of the function x plus the square root of x. And in order to differentiate it, it's probably convenient to write it as x to the 1/2. And I would like you to pause the video, give yourself a moment, differentiate this function. And recall, a key differentiation property is the power rule. The derivative of x to the n is always nx to the n minus 1. So in this case, g prime of x is going to be 1 plus, and if you use the power rule and you rewrite the derivative of the square root is always 1 over 2 square roots of x. And this quantity is always going to be positive. The reason it's always going to be positive is you have the positive number 1 plus another positive quantity. Remember, a square root only has positive, or let's say non-negative outputs. And based upon our previous observation, we can now guarantee that this function has an inverse. So since g of x is always increasing, its graph must pass the horizontal line test. And note, when we say its graph passes the horizontal line test, that's really just saying that g is a 1-to-1 function and it has an inverse. And that answers a question that we've been asked. So once again, just to kind of reiterate, if a function is strictly increasing or decreasing, then it is 1-to-1 and must have an inverse. From a calculus perspective, strictly increasing means a first derivative which is always positive. Strictly decreasing means a first derivative which is always negative. And this leads us directly into a second question. If we know a function has an inverse, how do we go about finding it? And it turns out the question of finding an inverse should be a familiar one from past courses, maybe say pre-calculus. And intuitively, you simply need to undo the function. That is to say, solve for x in terms of y. From a procedural standpoint, if it helps, I find it convenient to first switch around all of the x's and the y. So rewrite this equation as x equals f of y. And then once you've done so, undo the function. Solve for y as a function of x. Let's go ahead and apply this to a nice concrete example. Let's find the inverse for the function given by y equals the square root of 10 minus 3x. And if we see a question phrased in such a way of find f inverse for a given function, you can assume the function has an inverse. So let's go ahead and do this. The first thing we want to do is change around the role of x and y. So I'm going to write x equals the square root of 10 minus 3y. And then I would like to solve for y. So algebraically, we will step by step isolate y. We first need to get it out of the square root, so we square both sides. And then we would prefer to have, say, a positive coefficient for that y. So let's add 3y to both sides and subtract x squared. And then lastly, to isolate y, we divide by 3. So this would be 10 minus x squared over 3. And this quantity that y is equal to, that represents the function f inverse of x. So our conclusion, the function we've been asked to find, f inverse of x, is equal to 10 thirds minus x squared over 3. And the final thing I'd like to discuss in this video is just the graphical relationship that exists between a function and its inverse. So the graph of y equals f inverse of x is the reflection of the graph y equals f of x about the line x equals y. And let's look at a familiar example to help us visualize this. The function f of x equals x squared, as we noted previously, does not have an inverse. But f of x equals x squared with the domain sufficiently restricted, let's say for non-negative inputs, x bigger than or equal to 0, this does have an inverse. And we should be able to very easily visualize this graphically. F of x equals x squared for positive inputs would just be the right half of that standard parabola, y equals x squared. And I'm guessing you can probably tell me what the inverse of x squared would be. Thinking of the inverse as undoing the function, you undo a square with a square root. And graphically, we have y equals the square root of x. And we can now hopefully very clearly see the relationship between the graph of the function f of x and its inverse. They are reflections of each other about the line y equals x. This finishes our introduction into inverse functions. Where we would like to take this next time is begin thinking about how we can differentiate an inverse function and specifically introduce a formula for differentiating an inverse function at a point. So stay tuned, take care.